Hi guys, welcome back to my mathematics tutorial. My name is Peter C. Dogwood, your math tutor, and I am an instructor of mathematics at the University of Liberia. So in today's lesson, we want to start with finding derivatives of trigonometric inverse function, but particularly using the trigonometric substitution method. So in the previous lessons, we did not use the trig substitution method. We only found the derivative of the trig inverse function using several other methods like reducing the angle or just directly finding the derivative. But this one now we want to use the trig substitution to find the derivative of the trig inverse function. And the trig substitution is a kind of easier form of finding derivative of inverse function because most often you found out that the angle of that trig function is very large to deal with. So when you observe that, then you try to rewrite that angle. So that's exactly what we want to do. Now, the objective of using the trig substitution is to ensure that the angle is reduced to the similar trig function. That is, if this is tangent inverse, it means we need some tangent in here such that tangent inverse of tangent of an angle equals to that angle using the inverse property of the trigonometric function. So now, lastly, before venturing into finding derivatives of trigonometric inverse function using the trig substitution method, you must have some basic understanding of the trigonometric identities because you will have to substitute the variable with some trig function so that it leads to a trig identity. So if you don't understand the trig identity, there's a need to review the trig identity because the kind of substitution you use will aid you in the problem or might just get you going around a cycle. So the square root of 1 minus x divided by 1 plus x. Now what we know a trig function that is similar to this expression. That is 1 minus x. So that x could be a trig function. Now, we know that cos of 2x, or let's say cos of 2 theta, for example, is equal to cos squared theta minus sin squared theta. Now, if we replace this cos with the Pythagorean identity for cos of theta, which is 1 minus sin squared theta, we will have 1 minus 2 sin squared theta. So it means cos of 2 theta can also be expressed as 1 minus 2 sin squared theta. Also, if we rewrite this sign in terms of the Pythagorean identity, cos of 2 theta equals to cos squared theta minus, now this is now 1 minus cos squared theta. So we multiply this negative by every term, you have a negative 1 and you have a positive cos squared theta. So cos of 2 theta now will give us 1 cos squared theta plus 1 cos squared theta is 2 cos squared theta minus 1. So this is another identity that we can derive from there. Now, from the previous identity, if we send this term on the left-hand side of the equation, we will have positive 2 sin squared theta. And then this cos of 2 theta goes across. We have 1 minus cos of 2 theta. So you clearly see that 1 minus cos of 2 theta, 1 minus x. So we will replace this x with some cos of 2 theta. Similarly, if we do that for the next identity, that is, we send this 1 across the equal sign, we will have 2 cos squared theta. And then this is positive now, so it's 1 plus cos of 2 theta. Now we have these two important identities. But remember, our objective is to ensure that this entire expression ends up into tangent. So what do we also know? We know that the quotient identity for tangent is equals to sine of theta all over cos of theta. So with that in mind, we can now relate these two identities, that is 2 sine squared theta all over 2 cos squared theta is just equal to 1 minus cos of 2 theta all over 1 plus cos of 2 theta. So these two and these two cancel, right? So if we rewrite it by say cos sine of theta divided by cos of theta all square, because this is these two are square, right? And then we have 1 minus cos of 2 theta all over 1 plus cos of 2 theta. So if we take the square root on both sides, these two will go out. It means we will now have, let's bring it here. Okay, you just erase this one. So it means that we will now have sine of theta all over cos of theta equals to the square root of 1 minus cos of 2 theta all over 1 plus cos of 2 theta. But what is sine over cos? It's tangent. Tangent of 2 theta. So 1 minus cos of 2 theta divided by 1 plus cos of 2 theta. So this clearly shows that if we substitute x with cos of 2 theta, it means that we will learn into tangent of theta. Now you see that if you do the substitution in this problem that you are to try, you might get cot of theta. Because it will be like a reverse of this expression. So you will get cot of theta. Then you can bring in the co-function identity for cot of theta. Okay, so we say let x equals to, so let's put the substitution right here. Let x equals to cos of 2 theta. So we can solve for this 2 theta by taking cos inverse on both sides of the equation. Cos inverse of x is equals to cos inverse of cos of 2 theta. So cos inverse of x will just be equals to 2 theta. So let's keep this. We're going to use it. So now we have y equals to sine of 2. Now this is, okay, so it's 2 tangent inverse of the square root of now 1 minus, so that is cos of 2 theta all over 1 plus cos of 2 theta. So this entire expression is just tangent, so y equals to sine of 2 tangent inverse of tangent of theta. So if you just hold on to these two, tangent inverse of tangent of theta is just theta. So y now becomes sine of 2 theta. But the substitution tells us that x is equal to cos of 2 theta. And now here we have sine of 2 theta. So we cannot just use this. We have to rewrite this in terms of cos. But what do we know? Fundamentally, from the Pythagorean identity, we know that sine squared theta is equals to 1 minus cos squared theta. So we take the square root on both sides. It means sine of theta is just equal to 1 minus cos squared theta. Now this angle is a dummy variable. This theta represents a dummy variable. So if this is, for instance, 3 theta, it means this will be 3 theta. If this is 4 theta, it means this will be 4 theta, and so forth. So what if we allow theta to be equal to 2 theta? So if we say sine of 2 theta, it means we will get 1 minus cos square 2 theta. So we can now replace the sine of 2 theta with 1 minus cos square 2 theta. So y now equals to the square root of 1 minus cos of 2 theta all square. But what is cos of 2 theta? It's just x. So y equals to the square root of 1 minus x all square. So this is what we are about to differentiate. So you see how easy this will be if you just do the substitution instead of dealing with that complicated problem. You now have a simple problem to deal with. So now we find dy by dx. So we can first rewrite this as 1 minus x squared raised to the power 1 over 2. So to differentiate using the extended power rule, we bring this power down 1 over 2. We rewrite the expression 1 minus x squared. Then we subtract 1 from this power. So that gives us negative 1 over 2. Times the derivative of what is inside. The derivative of 1 is 0. The derivative of x squared minus x squared is minus 2x. So you see that this 2 can cancel this 2. We have dy by dx is just equal. Now this is negative. When it goes in the denominator, it becomes positive. So because it is half, it's still the square root. So we say the square root of 1 minus x squared. And in the numerator now we have x. So this is it. This is the derivative of this function in terms of x. This is the derivative. So thanks ever so much for watching. Please don't forget to like, subscribe, and share our videos. In the next lessons, that is over 10 different lessons, we're going to dive into more problems involving the trigonometric substitution method. So see you in our next lesson. Thank you.